Yeah, so in my lecture today I will talk about how to make DFT work in practice. And as you have heard in the two previous lectures, to do this we need approximations for the exchange correlation function. Now, I will first, in the first 3 minutes, give an introduction that is very similar to the two previous speakers, putting an emphasis slightly differently. And then I come to the main topic, which is the functionals. So we start with a Hamiltonian of condensed matter. That is atoms, molecules, clusters, and solids. Here it is, if you wish, the Hamiltonian of everything in the non-relativistic regime. So it consists of a kinetic energy of the nuclei, nuclear-nuclear Coulomb repulsion, kinetic energy of the electrons, electron-electron repulsion, and the electron-nuclear attraction. And with this Hamiltonian, in principle, at least, we have to solve either the stationary Schrödinger equation, or if there's an external driving field like a laser, the time-dependent Schrödinger equation. Now, this is a formidable task. The wave function and the Hamiltonian depends on all the coordinates of the electrons in the system, all the coordinates of the nuclei in the system, and everybody interacts with everybody else. So that's extremely hard. And the first approximation that one usually does is the Born-Oppenheimer approximation. And this is obtained by neglecting in this Hamiltonian the nuclear kinetic energy. So why would one do this? Why is this a good approximation? Well, one way of saying it is the nuclear masses are so large compared to the electronic mass that nuclei usually move more slowly, and hence the electrons kind of instantaneously adjust to the momentary position of the nuclei. And this is what, in fact, this Hamiltonian embodies. The nuclear coordinates appear only as parameters, like here, and the kinetic energy of the nuclei is gone. In a way, this is the infinite nuclear mass limit of the previous Hamiltonian. And so this many electron problem then has to be solved for each fixed nuclear configuration, capital R. So in this way, the wave functions, those are many body, many electron wave functions at fixed nuclear configuration. One imagines those can be obtained for each given nuclear configuration, and hence the eigenfunctions here and the eigenvalues become functions of the nuclear coordinates. So that's what we do for the electrons. And then we make as approximation for the full problem, for the full electron-nuclear wave function, this so-called adiabatic approximation. We imagine we have this guy, the Born-Oppenheimer wave function, for all possible nuclear configurations. We multiply it with a nuclear wave function and variationally optimize this guy by plugging this ansatz into the variational principle. And this leads to an equation of motion for this nuclear wave function, and here it is. So it is now a Schrödinger equation for the nuclei, kinetic energy of the nuclei, bare nuclear repulsion. And in addition, there are three potentials: a scalar potential, so it's a function of nuclear coordinates; another scalar potential, it's also a function of nuclear coordinates; and a vector potential. We call this vector potential because it couples to the nuclear momentum operator. Right? So two scalar potentials and a vector potential. This scalar potentials, this guy here, is the eigenvalue of the electronic problem. And the other scalar potential is the nuclear kinetic energy acting here on the nuclear coordinate dependence of the Born-Oppenheimer states. So it's a funny thing. It's not an operator in the electronic Hilbert space, It's something else that acts here on the nuclear coordinates. So this whole thing, since you integrate out the electronic degrees of freedom, is a function of nuclear coordinates, so it's a scalar potential. And then in addition, there's this vector potential, which has this structure, the nuclear momentum operator, acting again on the subscript here on the nuclear coordinates and integrating out the electronic coordinates. So this gives you this vector potential. It's usually called a Barry connection because in some cases, when you integrate a loop integral, a closed loop in the nuclear configuration space, you may get a Barry phase, a geometric phase. So this is a very interesting object. Whole books have been written about this. They correspond to topological features of molecules, these Barry phases. And but this guy is also important if, and many of you will actually have solved this equation, if you expand this potential, the scalar potential, and this one to second order around the nuclear equilibrium positions, right? To second order means that the Hamiltonian then, if you neglect the vector potential, reduces to a harmonic oscillator potential, gives you the phonon spectrum of the system. So a very important equation, but as input we need this total electronic energy and this vector potential as function of nuclear coordinates. So that's then the electronic structure problem, and this is what I will focus on. I should mention that after all, this is an approximation, right? This is not the full problem that I had on the first transparency anymore. This electronic many-body problem, which is still an exponentially hard problem, is already the result of an approximation. One can overcome this, and I just mentioned that at this point, if there's time at the end, which is unlikely, I might say a little more about this. One can make this adiabatic form of the full electronuclear wave function, one can make this exact by requiring not anymore that this is a Born-Oppenheimer state, but something more general. And one can then, first of all, prove that this is an exact representation of the full electronuclear wave function. And one can deduce equations of motion, which look pretty much like those. Like a nice Schrödinger equation for the electrons. And one can actually prove that the Schrödinger equation that you get gives you the correct nuclear n-body density and n-body current density. And these potentials are unique. And this means if you want to do classical trajectories, it is this generalized adiabatic form, which is exact, that should give you the forces. There's no choices. Those are the right forces. Okay, that was a question.
I have a question. Actually, you were mentioning adiabatic forces.
Yes.
I noticed the most crude one. Actually, there are much more. Why we are using this, for example, there is like Born-Mark adiabatic forces.
Yes.
Another one. So why we are using this one? That's the functional theory calculations. Is there any difference between them?
Well, Born-Huang expansion is another way of solving the full electronuclear problem, in principle exactly. Right? It's an expansion, but it's extremely hard to do in practice. Basically impossible to do for more than 6 or 8 degrees of freedom. So that's very little, right? So ultimately, right, you really have to, there's not, for numerical reasons, you have to treat the nuclear motion as classical motion, right? And then immediately you have a problem. What is the right classical force? Because if you have coupling of many Born-Oppenheimer surfaces, then it's difficult. What is the right classical force? There's only one classical force. That's the claim. And okay, but this is a different topic. This is not, as I said, if there's time in the end, I might come back. Okay, so this electronic problem in von Oppenheimer, this alone is already exponentially hard, as everybody knows. But it's sometimes useful to remember how quickly this exponential growth catches up with you. And I've put together here a little consideration. The oxygen atom. 8 electrons, so the many electron wave function for fixed nuclei, so we are now doing von Oppenheimer, depends on 24 coordinates, x, y, z for each electron. Okay, so this means it's a very big space, and let's assume we have a super hypercomputer by which we could actually calculate this wave function by solving the Schrödinger equation. And let's imagine we want to store it somehow on DVDs or disks, it doesn't really matter. So let's imagine we make a big table of the wave function. So how would you do this? Well, the most primitive way of doing this is to just discretize space, right? And, just store the wave functions at these discrete points, right? So let's think of one particle, hydrogen atom, right? So we have x, y, z, and let's say we discretize in x direction 10 points in space, y direction 10, z direction 10. So this is 10 times 10 times 10, 1,000 points on which we have to store the wave function. Now let's take the next step, helium. So that's x, y, z for the first electron, x, y, z for the second electron. That's 10 times 10 times 10, and another times 10 times 10, and so on. That's 10 to the 6. So since here the wave function depends on 24 coordinates, it's 10 to the 24 entries for this table. Let's be modest. So 1 byte per entry is 10 to the 24 bytes. And on a typical DVD, we can store 5 times 10 to the 9 bytes. So this requires 10 to the 14 DVDs. And I took the weight of a DVD, it's around 10 grams. So this means we need 10 to the 15 grams of DVDs, which is 10 to the 9 tons. Well, it's a finite number, but it's a lot. Put all the cars and trucks that exist in Europe on one heap and outweigh it with DVDs. Now, this is really the full wave function, right? But it's a very small system, just oxygen. Who is interested in the oxygen atom? Right? We want to do big molecules, proteins, and so on. And it's easy to see that the weight of DVDs that you need for a protein exceeds the weight of the universe. So it's a problem, really. But it's a problem only if you want the wave function at very high accuracy. Right? Usually this is not necessary. The wave function contains a lot of information, like n-body correlations, probability of finding one electron here, the next one there, the third one there, the fourth one there. Such n-body correlation functions are usually not needed. It's only if you want this very high-level information that you have this exponential growth. Usually, if you are more modest, if you want just an energy or so, and if you remember the expression for the total energy, it involves the two-body density matrix, so it's two-body correlations. So this might tell you that there's ways around it. Now, in view of this exponential problem, there's essentially two different classes of ab initio approaches. One class is called wave function approaches, and the philosophy there is, well, even though there's this exponential wall, let's try it anyways. And there's maybe these three most important ways of dealing with this: quantum Monte Carlo, configuration interaction, and tensor product decompositions. So that's one approach. Another approach that could be summarized on functional theories. And there the idea is that you write the total energy as a function L of a simpler quantity and then minimize. So this gives you then a variational equation ultimately for this simpler quantity. So what is this simpler quantity? Well, there's different choices. One choice is the Green's function. Let's say the one-body Green's function. This is normally called many-body theory or many-body perturbation theory, Feynman diagrammatics. But it's also a functional theory, if you think about it, because ultimately what you need is a functional of the so-called phi functional or the so-called self-energy as a functional of the Green's function. This is the input, this functional that you need. Another choice is reduced density matrix functional theory. So there you write the total energy as a functional of the one-body density matrix. This is actually a simpler quantity, right? You can get it from the Green's function if you wish by the equal time limit. So there you also have to invent an exchange correlation functional as functional of the density matrix. Or you can make density functional theory, and this will be the main topic, where you use the density as simpler quantity, and you have to find functionals for the exchange correlation energy or the potential. So in spirit, all these approaches are very similar, right, and totally different from wave function approach. Now, comparing these approaches to find a functional, a good functional that gives you good results in practice is relatively easy in the many-body context. For example, GW, right? A very simple functional, G times W. Couldn't be simpler, right? And in fact, it exists already for 50 years. For density matrix functional theory, it's difficult, more difficult, let's say, to find good functionals. And in the context of DFT, it's very difficult. It's very hard. So if you look back in history, progress is typically made on the scale of decades, right? The step from the LDA to the GGAs took something like 20 or 30 years. Now, the downside is that although here finding a functional is easy, to implement the approach in practice is numerically very heavy. Again, density matrices are intermediate, and for DFT, the numerical effort is relatively light. By no means trivial, right? There's several lectures on this, but in comparison. Right? Okay, so this will be the topic of my talk, and
Can I just ask, I think GW is not really good enough for many fields, right? For sure.
Absolutely.
Not for total energies. And improving this is also very, very hard.
Oh yes, yes, I know.
So it sounds a little bit too easy.
Well, it is. It's what I'm saying.
Theory, and if you don't start actually with a good start, you also lost.
Yeah. Then you might do it self-consistently, and then you get better total energies, but then you ruin the spectrum. I know, yeah, but at least it's an approximation that is simple, right? Exists for 50 years, and it takes you quite far. I mean, for certain quantities, like quasi-particle spectrum, not involving spin, then it's okay. Right? Still, for many questions, the gold standard. But, I mean, far from exact, no question. I mean, as you know, I live in an institute where 200 people are dealing with magnetism, and for magnetism, GW is just crap. It doesn't do anything. Yes, I'm well aware. Okay. Now let's focus on DFT, and so here's a summary of DFT in two statements. First statement is that the density is enough, at least in principle, to calculate every observable quantity of a quantum system. This, for the ground state density, is the Hornberg-Kohn theorem. And, well, this theorem alone is nice. Tells you if you give me the density, I can calculate everything from it, in principle. but this raises the question, well, from where do I get the density? Right? If I would have to calculate the density from the many-body wave function by solving the Schrödinger equation, there would be no gain. Right? So that's why we need the second theorem, that's the Cohen-Sham theorem, that tells you that we can actually calculate the density of the interacting system of interest from an auxiliary system where the particles do not interact with each other, they just interact with an effective external field, and that's then the Cohen-Sham potential. And these statements are so important that Walter Cohn, as you know, received the Nobel Prize for it in 1998. So here's a similar plot that Matthias showed, the increase in the number of papers that use DFT in one way or another as a function of year. This was done actually in a highly sophisticated way. This plot, the numbers slightly differ from yours. So that was mainly made by a computer scientist, David Gross, not related to me. So kilo papers is here the numbers. So by now, this is a bit outdated, it's about 36,000 papers per year. Just imagine what this number means, right? It's 100 per day, right? So this tells you, well, it's an enormously important and enormously successful theory. It also tells you that what I'm attempting here, namely to give a lecture on functionals, is a terrible task, right? Because it's obvious, nobody can have an overview of what has been done with functionals. There's no way of knowing, right? So if you make statements like I will make very soon that this functional typically leads to errors of 2% or so, for sure there's somebody in the audience that will say, well, I have the system where this functional give 50% error. So always happens. Right? And or if you say, well, this functional is good for that and not so good for other things, that there will be someone in the audience and says, yeah, but for my systems it's totally different. So for sure. So it's kind of an impossible task, but I'll try anyways. Okay, here's the Hohenberg-Kohn theorem again. We have this one-to-one correspondence. We have a variational principle. And this functional consists of a universal part and the part that contains the external potential of the system that we actually want to calculate. So that's the nuclear potential. And we always talk about functionals here. So just to remind you what the functional actually is, right, we have a set of functions, in our case usually the densities, and to each function you assign a number, right? That's called a functional. So a real valued functional, so that mapping is on the real numbers. There's a generalization of this term that we always use in the field of DFT, that this functional may depend on a set of parameters. Right? So which I put as an index here or in parentheses afterwards. That means that if you fix these parameters, then each function rho of r is mapped to a number, like here. But this number into which you map it depends on parameters. Right? There may be many parameters. So we say the potential is a functional of the density, or the Hohenberg-Kohn theorem says that the wave function is a functional of the density. Right? It depends on these parameters. Remember, usually we call this an operator. Right? If we map one function to another function, it's called an operator. But an operator is a special case of a functional, as you see here. That's why this field of mathematics is called functional analysis and not operator analysis. So functionals, that's the main thing. Okay, now here's something that is important to remember. When we say functional, this can be something very, very general. Right? If you just say, well, each function is mapped to a number. This can be, well, this is essentially, as Matthias called it, an algorithm. right? That we have to prescribe an algorithm that does that. Right? It's usually not something simple, like a function of rho of r or gradient rho of r. This is something much more general. And I'll give you an example for that. And that's the Hornberg-Kohn map. There's this simple proof by reductio ad absurdum, something very abstract that tells you that given the density, you can calculate uniquely the potential. Actually, for non-interacting systems, you can make this as an easy, simple algorithm. And that algorithm is here on this slide. Right? You just start from the non-interacting Schrödinger equation, multiply it with phi star, you get this, and then you see you get sum over phi star squared, which is the density here multiplying the potential. We divide by that, we get this equation. Right? That's just the Schrödinger equation. Nothing happened, nothing. Still the Schrödinger equation. So now let's define an iterative procedure that gives you, for non-interacting systems, the potential whose orbitals will then give you the prescribed given density. So that's the task. Given the density, what's the potential that yields this? So we start with an initial potential, solve, let's say, LDI, solve the Schrödinger equation, get the orbitals, orbital energies, and plug these orbitals and orbital energies here in the right-hand side, and divide by the density, but we divide by the given density, right? This is always fixed. So then, for that reason, it defines a new potential. We solve the Schrödinger equation again with it, get orbitals, orbital energies, plug them in here, divide it by the given density, get a new potential, and iterate this until we converge. And then the converged result is the Hornberg-Kohn map, explicitly. So it tells you, for example, if you have a good experiment that calculates the density, that measures the density, you can calculate the Kohn-Sham potential, the exact Kohn-Sham potential for it. No problem. Just this algorithm. And this means also that the orbitals that come from such a Schrödinger equation with a local potential can be viewed as functionals of the density, right? Because that's what you do here. You prescribe the density, you solve the Schrödinger equation, do this iteration procedure, get the potential, and get the orbitals. So the orbitals are functionals of the density. Okay, and here now finally the Kohn-Sham equation that you have seen, all of you, before. And so these equations yield the right density of the interacting system if you have the elusive exact functional here. And I quoted this place what Walter Kohn liked to say, that the Kohn-Sham equations are an exactification of the Hartree mean field equation. Exactification in the sense, and that's important to note, that the density that follows from these orbitals is the right density. Does not mean that the Slater determinant formed from these orbitals is in any sense an approximation to the wave function, to the full interacting wave function. By no means. Okay, so this functional, EXC, or the functional derivative, which is VXC, is a universal functional of the density, and this is the guy that needs to be approximated in practice. Let's just remember what means universal here. Universal means that this functional does not depend on the particular system that we want to calculate. Right? So the V0, the external potential that characterizes that system, there's no dependence on that here. V0 is here, but not here. So it's one and the same functional for all systems. For the hydrogen molecule, for the graphite crystal, for a sodium cluster. One and the same functional, just one functional. So this tells you, well, must be a pretty complicated object, at least the exact one. which is bad news in a way, which also tells you it's hard to approximate it. But on the other hand, it's also good news. There's only one object that you need to approximate. This functional, nothing else. Once you have a good functional, you're done. Right? Okay, let's now talk about explicit approximations. And, well, if you look at the size of the energy contributions, so here's this total energy expression, non-interacting kinetic energy, which is this usual kinetic energy expression with the density-dependent orbitals. And you look at the size of the numbers. Well, large numbers are this, and Hartree. They're about similar size. Then the exchange part is about an order of magnitude less, and the correlation part is, again, much less. So the exchange correlation energy as a number is a very small contribution to the total energy. Nevertheless, it's very important. But since it's small, well, the first idea that one might have is, well, let's neglect it altogether. That's the Hartree approach, actually not exactly the original Hartree approach, but the one that does not self-interaction correct. And so this is what people used in the pre-DFT times. Results are not good at all. Lattice constants and bonding distances are typically much too large. And that's why some people say, well, the exchange correlation energy is nature's glue. Right? It binds the atoms together. Right? It leads to a stronger binding. So then the next simpler approximation is the LDA. Here you use as input the exchange correlation energy as a function of the density. Right? So this object is the exchange correlation energy per particle of a uniform electron gas with density rho. And this object is known from Monte Carlo, from many-body theory, so that there exist approximations, parametrizations of it, so that you can consider as giving. So if you do that, you get, compared to Hartree, decent lattice constants, good phonons, surface energies of metals come out very well. So this was a major step forward, and that's why shortly after the invention of the LDA, essentially all solid-state physicists immediately accepted it. So this is a number of typical results. Atomic and molecular ground state energies better than 0.5%. Molecular equilibrium distances better than 5%. Band structure of metals, in particular Fermi surfaces, extremely good, few percent. Lattice constants, typically better than 2%. So that's rough numbers, but it's a guide. But there is a systematic error in LDA, namely that atomization energies are too large and bond length and lattice constants are too small. So this means that the LDA overbinds. It binds the atoms together too strongly. Nevertheless, these numbers, if you think about it, how crude and how simple this approximation is, right? It's kind of surprising. So naively, one would expect that the LDA works well only for systems that are weakly inhomogeneous. So clearly, for a homogeneous system, it becomes exact by construction. So weakly inhomogeneous is defined by these two conditions, that grad rho over rho should be less than the Fermi wave vector and less than the inverse Thomas Fermi screening length. But it is good, so these conditions are usually not satisfied everywhere in an atom or a molecule. So how come that it works for these strongly inhomogeneous systems like atoms still okay? I'm not saying it's brilliant, but it works okay. And the answer is that the LDA satisfies many exact constraints. So what is an exact constraint? That's a feature of the exact exchange correlation function L. Right? One can write down, and you will see such a representation, the full exact exchange correlation energy in terms of the many-body wave function. And from this way of writing it, one can deduce certain features of it. And it turns out that the LDA satisfies many of these features. So many of these exact features. Here I'm giving you a few. If you write the LDA functional in this way, in terms of the coupling constant average exchange correlation hole, what this is I'll come back to later. And then this object has to satisfy these constraints. So the integral over the exchange part is -1, integral over the correlation part is 0, and the exchange part is less than 0 everywhere. Those are important features. If you violate them, your functional will be crap. Okay, now still there's this systematic error in the LDA, and one would like to correct for that. The next generation of functionals are the so-called GGAs. Here the functional depends not only on the density at the local point R, integrated over, but also on the derivative. So this idea goes back, I think the first was Langreth and Mehl, then Becker, Perdue, Wang worked further on this, and currently the most used functional is, I guess, the PBE, the Perdue-Berkeley-Anserhoff functional. And how do you do this? How you construct a good functional? Well, it's this lesson that we have learned from LDA. You need to write down features of the exact functional, and in the construction of your approximate functional, you use those as constraints. So you try to satisfy as many such conditions as possible. This is a lesson that we have learned from LDA and also from the so-called gradient expansion. That's a nice way of writing the exchange correlation energy where you make a power expansion. So lowest order is LDA, then you get second order gradients, rho, then you get fourth order gradients and sixth order gradients. So it's nice and systematic, it appears. But if you truncate that series, results are much worse than LDA. And the reason for this is that you in fact violate this constraint. So this is what one understood. So it's important to satisfy that. And in fact, the first GGAs arose from kind of a gradient expansion, but then enforcing on top of that this condition, these three conditions. So it's known as real space cutoff. You cut off those parts of NX that are wrong, and then you get a decent result. Okay, now I'm not writing down here the parametrizations, by the way. You don't learn much of this, so you can look it up in the literature. Parametrizations, that's a second step. But the important thing is to know which constraints to satisfy. Now, if you do calculations, then you find that the GGAs reduce the LDA error in the atomization energy significantly, but not completely, while the bond lengths are overcorrected. So in GGA, bond lengths tend to be too large compared with experiment, while the atomization energies still are too large. And that's a problem. And so for that, we need to take a step further. I just want to make one historical remark here. Until the 90s, no decent chemist would ever use DFT. And the reason, well, rightly so, was that results with the LDA, in particular, the bonding distances were just not good enough for chemical purposes. Right? It was only the development of the GGAs that convinced the community of chemists that DFT is useful, and it was this one paper that did this job. So their comparison of 32 molecules was compiled. That's all the neutral diatomics that you can form from first row atoms, and you include H2 as well. And you calculate the atomization energies with these two functionals, Becker 88 functional and the LDA in Bosco-Wilk-Nozière, or here the Becker 88 with the LYP functional. And you compare the mean deviation from experiment and the mean absolute deviation, let's say with Hartree-Fock, and also with Möller-Plessis-Tooth, so that's second order perturbation theory, and results are much better. So in a theory that has an equation, the Cohen-Cham equation, that's actually easier in some sense than the Hartree-Fock equation, you get much better results. And this appeared like a miracle, but since John Popel was a very influential person, many people after this paper tried it out, and it was really this paper that got the stone rolling that ultimately led to the Nobel Prize for both Popel and Walter Kohn. But there are limitations. First of all, LDA and GGAs contain spurious self-interactions. So what is a self-interaction? Imagine the Hartree energy, rho of R prime divided by R minus R prime. And imagine each rho of R prime written in terms of Cohen-Cham orbitals. Then you have an interaction of phi 1 squared with phi 1 squared, with itself. That's called a self-interaction. Such terms should not be there, and they're in Hartree-Fock cancelled by self-exchange. But in approximate functionals, this cancellation doesn't happen, or happens only approximately. And this so-called self-interaction error has a number of consequences. Like for finite systems, there are no Rydberg states, no Rydberg series. Negative atomic ions typically are not bound. So small, very small systems, negative ions are not bound. This is because the asymptotic form of LDAs and GGAs is such that it does not decrease correctly as 1 over R. That's another feature of the exact functional. For finite systems, it should decay like 1 over R. In LDA, GGA, it does not. And ionization potentials tend to be too small if you calculate them from the highest occupied orbital energy. Then dispersion forces are not described. I'm not going to talk about this. That will be a whole talk of its own. Band gaps, if you calculate them from the Cohen-Cham HOMO-LUMO gap, are too small, typically half, on the order of half of the experimental gap. And then there's this energy structure dilemma that I mentioned before, that atomization energies are too large in GGAs, but bond lengths are also too large. And to the best of my knowledge, there's no GGA that can fix both of these simultaneously. So there's this PBE Sol, one version of the PBE that improves atomization energies but makes bond lengths worse. So this is still a problem. And then there's another problem of totally different nature, that's so-called strong correlations, that certain solids, which are antiferromagnetic insulators in nature, are predicted to be metals in Cohen-Cham. I should say, from the fundamental point of view, that's not a problem. It may certainly be that the Cohen-Cham system is metallic, but leads to a density that reproduces the density of an insulator. Why not? It's just then a very unnatural description of that system, right? If you want to deal with response functions or so, you're very far away with your Kohn-Sham estimate. Okay, so then let's take one step further. And how many times do I have? 5 minutes? Okay, that's the meta-GGA. Here, in addition, you choose a dependence on the non-interacting kinetic energy density. So that's this expression here. So energy density tau of r, whose integral gives you the non-interacting kinetic energy. And this more general form of meta-GGAs indeed solves this energy structure dilemma that the GGAs have. So here's this Jacob's ladder that we have seen before, LDA, GGA, meta-GGA. And then there's two more rungs that I want to discuss. Hybrid functionals, where in addition the functional depends on occupied orbitals, and the highest rung is occupied and unoccupied orbitals and the energies. So hybrid functionals. Here I first have to take a step back and explain what the so-called coupling constant integration or adiabatic connection formula is. Here you start with your full Hamiltonian and multiply the interaction with a lambda, that is between 0 and 1. That means once that lambda is 0, you have switched off the interaction between the electrons. But then you make your external potential also lambda dependent, and you do it in such a way that the density, so the lambda dependent density, actually does not depend on lambda. So you choose your potential such that the density stays constant, namely equal to the true density of the interacting system. Then you see immediately when you do that, that at lambda equals 0, when the interaction has disappeared, you get the Kohn-Sham potential, right? Because the Kohn-Sham potential is that potential that gives you the fully interacting density. While at lambda equal 1, you are back to the nuclear potential. So you imagine you could solve for each lambda the fully interacting system, giving you a lambda-dependent many-body wave function. And in terms of this lambda-dependent many-body wave function, which defines this quantity W lambda, you can represent the true exchange correlation energy as such a coupling constant integral. So that's an exact way of writing the exact function now. And you see this quantity W lambda at lambda equals 0. This wave function reduces, as I said before, to the Kohn-Sham determinant. So W naught is actually the Hartree-Fock exchange. And one can also evaluate W naught prime, which turns out to be the correlation energy in second order Girling-Levy perturbation theory. This is a particular version of perturbation theory where you again keep the density constant. And then, well, Becker had the idea, why not approximate the lambda dependence just as a linear dependence? Well, it's the first guess. And then, if you do that, and this is the so-called Becker half and half functional, you do the integration and you get this expression for the exchange correlation energy, where W naught, as I said, is the exchange energy, and W1 is a correlation part that you treat with some, let's say, GGA. So then you get this functional that is a mixture of Hartree-Fock exchange and a density functional approximation. And there's, in the same spirit, several other functionals on the market. They're all called hybrids. Here the PBE0, which is 25% Hartree-Fock exchange, 75% PBE for exchange, and the full PBE functional for correlation. And there's the B3 lip functional, where you take certain fractions of LDA and GGA exchange. Another way, a systematic way in a sense of constructing hybrids, is the so-called range separation, which is an idea that goes back to Savin. and was further developed by Roy Baer and Neil Kronig recently, where you write the full Baer-Coulomb interaction in this way with the error function and the complementary error function. So you split the full Coulomb interaction in a short-range part and a long-range part. And then, since you know that the long-range part gives you this 1 over r form of the functional, it's reasonable to require that the long-range part is treated by wave function theory, Hartree-Fock, or Andreas Savin has also done something better, and the short-range part with a GGA. So this is a reasonable choice for finite systems. For solids, it makes sense in a way to do it the other way around, to treat the long-range part with DFT and the short-range part with exchange. And that's the HSE functional, which is written down here. So one takes short-range interaction here and writes down the Hartree-Fock energy for it. And this then depends on this mu parameter and mixes in then some GGAs. So let's see what the final rung looks like. Here one could use perturbative expressions, MP2, that involve both occupied and unoccupied orbitals and orbital energies. RPA functional is of that kind. So typically that's functionals of the Cohen-Sham-Green's function. The Cohen-Sham-Green's function itself is a functional of orbitals. So in this way, if you take your favorite perturbative expression, you can get functionals of orbitals. And you can go beyond RPA by including vertex corrections and other sophisticated things. For example, you could also put it together with linear response TD-DFT by using this expression. It's another exact way of writing the exchange correlation energy exactly as a coupling constant integral that involves the coupling constant dependent response function. And this you can get from linear response TD-DFT, and all you need is then an approximation for this kernel here. Plug this in here, and you get a beyond RPA functional. Now, that's the kind of functionals we have. Now, once we are given such a functional, what do we actually do with it? And there's actually, once you're given such a functional, 5 different ways of dealing with it. So here they are. First way is to use them non-self-consistently. So you're given that functional, and you do it post-LDA, post-GDA, or post-Hartree-Fock, let's say. You do a Hartree-Fock calculation for that system, and plug in the density and the orbitals of that Hartree-Fock calculation into the functional. So non-self-consistently. Usually that's not so bad, if you think about it. Why is that? Well, what you should do is to do a self-consistent calculation to get the true minimum of total energy, right? But it's the minimum that you're interested in. Now, at the minimum, the derivative is 0, right? It's flat. It means that if you're slightly at the side, it doesn't really matter so much, right? Deviations are quadratic. Okay, then, for example, Axel Becker, in all his constructions of functions, he never did a self-consistent calculation. Always post. Then, self-consistent Cohen-Sham calculation, but with an orbital functional. So then we have to face this problem that orbital functionals are implicit density functionals. So we have to take the functional derivative with respect to that implicit density dependence. So what you do here in practice is you're given this total energy functional as a functional of orbitals, and you find the corresponding Coulomb potential, which is that local potential whose orbitals minimize that given total energy functional. That's OEP. It's called optimized effective potential method because it's ultimately a variation with respect to the orbital with respect to the potential that you do. Another way is to do it self-consistently, but with the so-called generalized Coulomb scheme. What you do there, given the total energy functional, you take the variationally best orbitals. So you just take the variation with respect to the orbitals. In this way, you usually get a non-local potential, right? Compared to this one, right? And I'll show you some numbers later. Here, you do a restricted minimization. You restrict the orbitals to come from a local potential. Right? That's a restriction. And then within this set of possible local potentials, you minimize. Here you don't do this restriction, you just freely minimize. Right? So you get a slightly lower energy in this way. Okay, now there's another way which rests on the Guidopoulos variational principle. This targets a very it's not terribly well known, but it, I believe, deserves much more attention. It targets a very specific problem that you have with these two approaches sometimes, namely when your function L comes from a perturbative expression. So, like this MP2 things here that we had before, right? It's far away. Doesn't matter. So you have these energy denominators, right? Now what do you do if you want to minimize the total energy? Well, you find that potential that makes these energies almost degenerate, right? So you minimize to minus infinity for this type of functionals. You don't get this in Hartree-Fock, but for perturbative functionals, you go to minus infinity by bending your potential in such a way to make states degenerate. It's not what you want. This is called variational collapse. And this is avoided by this Guidopoulos variational principle. Okay, and then there's yet another way, specifically for functionals that come from an approximation of the self-energy. And this is not to minimize an energy, but rather to find that local potential whose density reproduces the density that comes from the Green's function. It's yet another way. All these schemes are different. Right? They really don't give the same numbers. Okay, this is numerically very cumbersome. Very few people have ever done this. We did this in some context for superconductors, but I won't have time to talk about that. So here is a big table, but you could talk an hour about this, comparing many different functionals. What I want to show you here, just that this left column is post B3 lip, and the right is post PBE, so a GGA and a hybrid functional. And it confirms what I said before, that actually if you do it post something not self-consistent, it's not such a bad thing. Deviations are very similar. Here's this OEP equation. You have to solve this equation, where here enters the functional derivative of the given orbital functional, and solve this simultaneously with the Coulomb equation. It's numerically very delicate and difficult, but can be done. Solves many problems, like the self-interaction things for finite system. It's a local potential, but it comes from this integral equation. Generalized Coulomb, where you freely minimize the orbitals, you have a non-local potential. But you just do this, right, like Hartree-Fock. So it's numerically much easier. And if you look at quantities that are derived from total energies, then differences between generalized Kohn-Sham and OEP, different functionals, are very, very small. So the message is, this is delicate numerically, this is much easier. So you would be crazy to do this, right? So this is the preferred approach. And not only that, so this is what I wrote down here. In addition, it has one big advantage, the generalized Kohn-Sham scheme, namely, it also, the single particle orbital energies give you good gaps. And one can understand why this is the case. At least the best hybrid functionals give you that. And so there's only advantages of generalized Kohn-Sham over OEP. And this is an important message that I want to make here. So this is a recommendation to you if you use this higher rung functionals. Generalized Kohn-Sham is the way to do it. Yeah. Okay, and this is the last topic which I will talk about in the coffee break.
Thank you.